It is my distinct pleasure to introduce to you Karen E. Willcox, Director of the Odin Institute of Computational Engineering and Sciences and a Professor of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin. Karen holds the W.A. Tex Moncrief Chair in Simulation-Based Engineering Sciences and the Peter O'Donnell Centennial Chair in Computing Systems. Prior to joining the Institute in 2018, she spent 17 years as professor at MIT, where she served as professor of aeronautics and astronautics. She was founding co-director of the MIT Center for Computational Engineering and associate head of the MIT Department of Aeronautics and Astronautics. In addition to her many research pursuits, Professor Willcox is an active in education innovation. She served as co-chair of the MIT Office of Education Policy Initiative and co-chair of the 2013-2014 Institute-wide Task Force on the Future of MIT Education and the chair of the Open Courseware Faculty Advisory Board. She holds many honors. She's a fellow of SACM, fellow of AIAA, member of ASEE and ASME, served in multiple leadership positions in AIAA and SACM, including leadership roles in the SACM Activity Group on Computational Science and Engineering and the AIAA Multidisciplinary Design Optimization Technical Committee. She's an editor of the SACM Journal of Scientific Computing and associate editor of the AIAA Journal. Currently, she's a member of the National Academy's Board of Mathematical Sciences and Analytics and serves on 4 National Academy studies. In 2017, she was awarded the New Zealand Order of Merit and from her home country. Karen, it's a great honor to have you, and you can kick off this with the first plenary lecture. Thank you.
All right. Well, thank you very much, Tinsley, for the introduction. I can't tell you what an honor it is to be here to give this opening plenary and also to join John in welcoming you all here to Austin. So as of Thursday, Austin will have been my home for 1 year. And it really is an amazing place, not only the barbecue and the food and the outdoors, but of course it's, I think, one of the central places in the world for computational science and engineering, for computational mechanics. And I have to say, it's really the most remarkable place that I've been in my career, and I really, really love it here. So today I'm going to talk about some of the work in my group in model reduction, the work that's really at the interfaces of computational science and engineering and machine learning. But before I do that, I wanted to just make a couple of other remarks. Let's see if this thing's going to work. Okay. Technology has a way of working in the test, but not the execution. All right, we'll go manual. Okay, so as you might have gathered, ISIS is no more. The Institute for Computational Engineering and Sciences, or ISIS as it was known, is no more. So 2 months ago in May, President Fenves officially conferred upon the Institute our new name, the Odin Institute for Computational Engineering and Sciences, or for short, just the Odin Institute, or just Odin, as long as Odin the man is not in the room and can't be confused. But really, it's just incredible that we were able to rename the Institute and to recognize everything that Tinsley Odin has done for the Institute, for the University of Texas, and far beyond, really doing so much to lay the groundwork for the field. So just with, I think, several hundred of your closest friends here, Tinsley, maybe we could just congratulate Tinsley on this honor. And the other quick note I wanted to make is you would have seen in the program that there are many symposia honoring lifetime achievements of Professor Mary Wheeler, one of the other incredible faculty members who are part of the Odin Institute. I'm not sure if Mary is here this morning. It's a big room, and oh, there she is, waving her hand. So again, congratulations to Mary on incredible lifetime achievements, although as we noted last night at the banquet, Mary is not done, and we're looking forward to many more achievements to come. But congratulations, Mary. Okay, so with that, let me get to the plenary. First up, I wanted to just point out the folks from my research team who have contributed to the work that you're going to see today. And I have to say, I love pointing at screens, and it's important. Not only is there a choice of which screen to point at, they're too far away and angled very badly, so I'll gesture towards them. So Dr. Boris Kramer, who's a postdoc in the group. Boris will be starting a faculty position at UC San Diego next month, and Boris is here somewhere in the audience. Elizabeth Chan, one of my current MIT PhD students. Renee Swisschuk, who just finished her master's degree at MIT. Benjamin Pierstoffer, former postdoc from the group, who now is assistant professor at Courant. And Parisa Kodabakshi, who is a current postdoc here at UT Austin in the Odin Institute, and Parisa is also somewhere here at this conference. So here's what I want to cover today. I'm going to start off with a little bit of sort of a high-level vision on the notion of predictive data science. What is it, and why is it something that's needed? Then in the technical part of the talk, I'm going to go through a method that we're calling lift and learn, which uses the lens of projection-based model reduction as a way to learn predictive models. I'll show you some results for a very challenging problem in rocket engine combustion, and then I'll wrap things up. So first off, predictive data science. What does this term mean? What is it? And why is it needed? So clearly, I don't have to alert anybody in this room to the fact that data science is everywhere. The field of data science has exploded. We see it everywhere. We see it in almost every call for funding that seems to come out, certainly in the US. And we might ask the question, why is it that data science has exploded so much? And clearly a big part of the why is because there is so much data available, whether it's simulation data or observational or experimental data. And there's also been tremendous advances in computing power and in the algorithms. So the data, the computing, and the algorithms, that's a big part of the explosion. But I think it's much more than that. There's another reason for the tremendous excitement and indeed a lot of the hype around data science and machine learning. And I think that's because of the incredible success that we've seen of data science and machine learning for applications in computer science. So applications like social media, online retail, online gaming and entertainment, speech recognition, image recognition, and more. And with that incredible success and that incredible impact on people's lives has come a tremendous amount of excitement in taking those methods and bringing them over to important applications in science, engineering, and medicine. And on the one hand, that's exciting. This is exciting to think about. But on the other hand, it's something that should really give us pause and should, I believe, give us some concern. And the reason it should give us concern is because important high-consequence applications in science, engineering, and medicine are very, very different to the applications in computer science where data science and machine learning have been so successful. And in particular, the applications that many of us in this room focus on are a very high consequence. So the decision about designing the structure of an aircraft wing that's going to carry hundreds of people across the Atlantic is a very different consequence to the decision about which movie to recommend to somebody watching Netflix next. The decision about whether or not to remove the prostate of a cancer patient is clearly of very different consequence to the decision about recommending a next group of friends to a social media user. So again, this separates many of the applications in science, engineering, and medicine. These are high consequence decisions. These are big decisions. And these big decisions need more than just big data. These big decisions have to rely on predictions. And to paraphrase the very nice paper by Coveney, Doherty, and Highfield, and I hope Ed Doherty is maybe somewhere here in the audience, these big decisions really need big models too. They need the power of predictive physics-based models. So there are many, many examples of big decisions across science, engineering, and medicine where the data is not enough. I've got a few up there on the slide drawn from Odin Institute research. To pick just one, let me highlight the work of Clint Dawson's group, again from the Odin Institute, who are creating predictive models for hurricane storm surge. And clearly, these models can inform big decisions, not just the big decisions about if, when, and how to evacuate millions of people in the face of an event, but maybe even more importantly, the big decisions about the billions of dollars that are being invested in coastal infrastructure and in protecting the coast of states like Texas. And these big decisions about investment, of course, there's a lot of data that can be collected before, during, and after hurricane events, but those data really just tell us what happened in these isolated events. The data are not enough to issue the predictions to help decision makers identify where are the most vulnerable communities along the coast, and again, where is it that you invest billions and billions of dollars in building infrastructure that can protect against future events. So that's an example of a big decision that needs more than just the big data. These kinds of decisions, these decisions in science and engineering and medicine, have to incorporate the predictive power, the interpretability, and the domain knowledge of physics-based models, of mathematical models. And so this is the notion of predictive data science. Predictive data science needs a convergence of the field of data science and the field of computational science and engineering, CS&E. So computational science and engineering, CS&E, it's a field that at its very core is about using mathematical models to understand and reason about the physical and natural world around us. And again, I think it's very, very important in all this excitement in bringing data science and machine learning to bear on high consequence applications in science, engineering, and medicine. We have to bring the CS&E, we have to bring the mathematical modeling, the physics along into the problem. So one of the things you might ask, or maybe not folks in this room, but a computer scientist might ask, do you really need the models? Do you really need the physics? Isn't it just a matter of collecting more and more and more data? And again, I think we have to come back to the point that these applications in science, engineering, and medicine are very different to the applications in computer science, where data science and machine learning have been so successful. And of course, there are many, many differences. I'm listing here 4 that I think are the most critical. So the first is that these kinds of applications in science, engineering, and medicine are typically characterized by complex, multi-scale, multi-physics dynamics, the kinds of problems that John Shadid had an incredible career building large-scale simulation tools for. And so why is that important? That's important because these are problems where if you change the parameters just a little bit, if you change the initial conditions or you change the properties of the system, the dynamics can vary wildly. And this is especially true when the systems are close to the most critical conditions for decisions, when the system's close to instability or close to failure. And so if you have an approach that simply tries to interpolate data, no matter how much data you have, or even worse, tries to extrapolate data, then you're in real trouble. You're doomed to failure. Second, these kinds of applications have high-dimensional parameter spaces. And in fact, for many of the systems in the physical and natural world, the parameters that we have to characterize are infinite dimensional fields. When we discretize those problems, we get problems with millions or even billions of degrees of freedom. Now, we know that solutions often lie in much lower dimensional manifolds, and in fact, that's what the physics, what the governing laws of nature do for us. They define low dimensional manifolds where solutions are constrained to live. But if you have an approach that's based on the data alone and you're looking at the apparently billion dimensional space, again, you're in real trouble. You're doomed to failure. Third, we talk about big data, and indeed, we often do have a lot of data for the system. But again, for these applications in science and engineering and medicine, the data are usually relatively sparse, especially compared to the dimension of the parameters that need to be characterized. And it's not just a matter of getting more data. The data are intrusive, especially if you're talking about measuring things about human beings, about patients, or about sending sensors out into the natural world. The data are intrusive and they're expensive to acquire. And then the fourth point is that uncertainty quantification is absolutely key. I can't think of a high consequence decision in engineering, science, and medicine that does not rely on our ability to predict into the future, to predict the climate in decades to come, to predict in situations where we really cannot reasonably hope to have a large amount of training data. But we have to make those predictions. We have to quantify the uncertainties associated with those predictions, quantify the confidence, and build that into our decisions. So again, predictive data science, convergence of data science and computational science and engineering. And I'm sure there are many folks in the audience who sit there and think, well, this is great, but is this new? Isn't this the way that we as computational scientists have really approached challenging problems for many decades? And the answer is absolutely. This is the way that many of us have approached problems for a long time. This notion of learning from data through the lens of models, in fact, sits at the very heart of so many of the methods across computational science and engineering. Inverse problems, Bayesian inference, dynamical systems, approximation theory. There are so many elements of applied mathematics, of computational science and engineering, of computational mechanics, optimization, and so on, that really, again, have at its heart this notion of learning from data through the lens of models. But it's not all old. There certainly is new thinking that comes from the perspective of computer science, from data science, and from machine learning. And in particular, what I hope to show you in the next part of the talk, in the technical part of the talk, is that there are ideas we can take from the machine learning world, and in particular, the flexibility of learning from data, put those ideas together with the notions that we've had in our community for many decades, to come up with methods that are more powerful, that really let us advance and tackle some of these very challenging problems. And I'll do that in talking about some of the research from my own group in the field of projection-based model reduction. So onto the second part of the talk, and it's very nice to have the extra time. That's good. I'm sure I'll use it up. So I'm going to talk to you about a method that we call lift and learn. And again, it's using projection-based model reduction as a lens through which to learn predictive models. So I'm going to need a whole bunch of ingredients, and I'm going to go through the ingredients one at a time and then show you how they come together. So the first ingredient is going to be a physics-based model. And for the problems that we're interested in, these physics-based models typically manifest themselves either as a coupled system of partial differential equations, PDEs, or maybe large sets of ordinary differential equations, ODEs. And I have a couple examples up there on the slide. An example of rocket combustion, which is the one that I'll show through the talk. And then at the bottom there, an application in additive manufacturing, which is some of the work that Parisa is working on, and this is, we're applying the similar ideas, trying to apply similar ideas in this setting. So the first ingredient is a physics-based model. The second ingredient is going to be the notion of projection to define a low-dimensional model. Third, we're going to think about variable transformations that expose particular structure in our model. And then fourth, we're going to bring in the data-driven machine learning perspective of non-intrusive learning, learning the reduced model from data, but using all the ingredients that come above. Okay, so the first ingredient is the physics-based model. And as I said, for our problems, these physics-based models usually come in the form of PDEs or ODEs. I don't expect you to read the equations, but again, just to remind you that the systems of PDEs that govern nonlinear multi-physics, multi-scale phenomenon like the rocket combustion problem are complicated. There's a lot going on. These equations embody the laws of nature, conservation here of mass, momentum, energy, and conservation of the species. So I'm going to work in the model reduction part of the talk. I'm going to work with the spatially discretized system. So imagine taking your set of PDEs and discretizing them in space with your favorite spatial discretization method, finite elements, finite volume, finite difference. And if you were to do that, then you would get to a system like the one there in the middle of the slide, which is now a very large set of ODEs. X there is the state. This is the discretized state. So for this rocket combustion example, the state there, x, has got the density, momentum, energy, and species discretized over the spatial domain. So x is a vector of very high dimension of millions of degrees of freedom, again containing our discretized unknowns. Then the rest of the terms in the equation, so E, a mass matrix, AX, the term representing the discretization of the terms and the PDEs that are linear in the state. U there is a forcing input, so BU represents the effects, for example, of boundary conditions on the system. And then F of X and U, all the nonlinear terms that didn't fit into A and B. So there's our physics-based model. And again, those physics-based models, those large-scale discretizations are very, very useful. But in many settings, they're too big and they're too expensive. And just to give you a concrete example, the rocket combustion project that we're working on, so we're working with a code, we're working with an Air Force Center of Excellence, and I should say the US Air Force has invested a lot of time and effort and money in developing large-scale CFD simulations for rocket combustion over the last decade. And they've got incredible capabilities now in terms of what they can simulate. But to do a full 3D simulation of an entire rocket engine is estimated would take 3 months on a supercomputer to do just one simulation. And of course, the goal is not to do one simulation. The goal is to do many simulations, exploring design choices, parameters, different control settings, different fuel injection strategies. But when a single simulation takes 3 months, clearly you cannot do very many studies in your design. And so this is where model reduction comes in. Model reduction says we have these big, complex discretizations of the PDEs, but they take minutes or hours, or even in this example, months to solve. So then the question is, can we come up with simpler, smaller, cheaper models that can solve much faster, but in some way provide principled approximations, good enough approximations to, say, be able to explore the design space? So this is where projection-based model reduction comes into play. There are 3 main steps. The first, the training, which is to generate representative solutions by solving that large-scale model. And we're going to generate training data that are typically called snapshots. These are state solutions. Second is to identify structure, compute a low-dimensional manifold or a low-dimensional subspace in which the key dynamics resolve. And in what I'll show you today, we use the proper orthogonal decomposition, the POD, to compute a low-dimensional basis that defines a linear subspace. And then the third step is to create the reduced model by taking those large-scale PDEs and projecting them onto the low-dimensional basis to define the reduced model. So mathematically, how does that look? There at the top of the slide is a full-order model. Let's look first at the linear model. So I've dropped off the nonlinear term, the f of x and u. Here's a model that's linear in state. So there's our full-order model. Remember, the state x is the discretized unknowns. It's got very high dimension. Think millions of unknowns. We identify the structure. We're defining this low-dimensional subspace defined by the basis matrix V. And we're going to approximate this high-dimensional state x in the low-dimensional subspace V. So we do that by replacing x with V times x reduced, xr, where xr has the coefficients of the expansion in this basis V. We can substitute that into the governing equations, into the full model. We now have n equations, just r degrees of freedom. So we'll have a residual. We can then do a Petrov-Galerkin projection or a Galerkin projection. And in this talk, I'm going to work with Galerkin projections. So setting W there equal to V. And in doing so, define the reduced order model at the bottom of the screen. And what you notice is that the reduced model, E reduced, X reduced dot equal A reduced, X reduced plus B reduced U, has the same form as the full model that we started with. Instead of solving for the million-dimensional state X, we're now solving for a much smaller dimensional state X reduced. And these reduced order matrices, the E reduce, A reduce, and the B reduce, are just these relatively simple projections of big E, big A, and big B onto the low-dimensional subspace defined by the basis V. So a very simple notion of projection, but very powerful. You might ask, okay, what happens when the nonlinear term is in there? So remember in the nonlinear equations, we had that f of x and u term. So notionally, we can go through the same steps, approximating the solution in a low-dimensional subspace, again, the basis matrix V, substituting in, taking the residual, performing a Galerkin or a Petrov-Galerkin projection, and we get to the reduced model there at the bottom of the screen where we now have the nonlinear term F reduced. But if we look carefully at F reduced, we see it's V transpose F of V X reduced. So in order to evaluate F reduced, we have to take our reduced order state X reduced. We have to blow back up to the full state X. We have to evaluate F of X at the full state, million dimensional, and then project back down to the subspace. And so this is a well-known limitation of nonlinear model reduction, that the nonlinear terms don't have this offline, this compact representation in the projection. Now, of course, there are many methods in the literature that have been proposed to deal with that. I'm going to show you a different approach in what we're getting to in just a second, but we'll keep this in mind. But again, just to come back to the linear model and to make a couple of important points, there's the linear model, full model, and reduced model. And again, remember that the projection framework preserves the structure, and those reduced matrices, A reduced, E reduced, and B reduced, can all be pre-computed. You give me A, B, and E, I take the basis V, and I give you back A reduced, B reduced, and E reduced, and you have your reduced model, and you're good to go. So the same is true for the quadratic model. If we were to introduce a quadratic term, you see there the H, X cross X, where X cross X is notationally indicating all the quadratic products of states, then projection preserves the quadratic structure, and in fact, A reduced is now V transpose H of V cross V. It's a little bit more complicated, but again, it can be pre-computed. And you could probably imagine that if we went out adding cubic, quartic, and higher order polynomial terms, the projection framework would preserve the polynomial structure of the full model. So we see that projection preserves structure. And why is that important? That structure is not arbitrary. This A and H form is not arbitrary. Remember, these operators are the discretized terms of the partial differential equations. And the reason that there's an AX in the equations is because there's something like a linear diffusion process in the governing equations. The reason that there is a quadratic HX cross X is because there's something like a UdUdx in the partial differential equations. So these operators, this structure, are embodying the physics, the governing laws of nature, and projection preserves the structure. And again, I think this is a really important point to recognize when we're deriving reduced order models through this lens of projection. Okay, so just to close up with one last comment on projection-based reduced models, you might ask, what is the connection between reduced order modeling and machine learning? And the go-to place for such questions is Wikipedia. So there are the Wikipedia definitions. So machine learning is a field of computer science that uses statistical techniques to give computer systems the ability to learn with data without being explicitly programmed. For reduced order modeling, it says model order reduction is a technique for reducing the computational complexity of mathematical models and numerical simulations. So when you read those, they sound very, very, very different. My own view is they're really actually not that different, that the difference comes from the perspective, and you can see the perspective, the origins of these fields. Machine learning has come from the computer science community, where there's a pile of data, and the goal is to learn a model that explains the data. Reduced order modeling has come from the CS&E community, where we start with a big model, and the goal is to reduce that model to find a low-dimensional model. And the reason, by the way, we start with the big model is because we're starting with physical models, with PDE systems or with large systems of ODEs. So the perspectives and the origins are different, but at the core, the fields are actually very closely related, and not just philosophically. When you start to dig into many of the methods, you think about the proper orthogonal decomposition and the PCA, the principal components analysis. The SVD sits at the heart of so many of the methods that find low-dimensional structure, and the same is true for many other aspects of methods that are used in these fields. So different perspectives, but with different perspectives comes a lot of value, comes new thinking. And what I'm going to show you what's coming next. Putting those two different perspectives together, we believe is a way to come up with even more powerful methods than what we have. Okay, so we've got a physics-based model. We've got a way to define low-dimensional models through this notion of projection. The third ingredient is an ingredient of variable transformations in lifting, which is to say that we don't have to work with the physical governing equations that come out of the textbook. We can use these governing equations and manipulate them. We can identify variable transformations that expose system structure. And in particular, we're going to look for polynomial structure because we know that polynomial structure can be preserved under projection. So I'm going to explain this piece of the talk just through examples. And let me put up an example that I hope is pretty familiar, which is the Euler equations. So here in 1D, the equations describing compressible inviscid flow. So we already know that there are multiple ways to write the Euler equations. There at the box on the left is the most common way, writing the Euler equations, conservation of mass, momentum, and energy in the conservative variables, mass, momentum, and energy. And there with the equation of state relating their pressure and energy. But we know we can write the Euler equations with primitive variables. So the primitive variables, their density, velocity, and pressure. And the equation, so let's not think about problems with shocks, but think about problems where the derivatives are all defined. Those are just different ways to express the same governing conservation equations. So also what is well known in the fluids community, but not often, not used, apparently not used all that much, is that we can write the Euler equations in specific volume form. And a specific volume, I'm going to call it Q, is 1 over the density. So if we'd like to use specific volume as a variable, we can apply the chain rule and derive the evolution equation for dq dt. And then we can get to the specific volume form of the Euler equations, where now the specific volume variables are velocity, pressure, and 1 over density. And what do you notice about the PDEs in that bottom box? If I work with the variables WP and Q, velocity, pressure, and 1 over density, the equations are exactly quadratic in those variables. And again, that's something that's known in the fluid dynamics community, and there are some solvers that exploit this. But now when it comes to model reduction, recognizing that the choice of variables we work with means that the system takes on a different nonlinear form is very, very important as we think about preserving structure and deriving models. So notionally, we're not going to, but notionally, if we were to discretize the quadratic form, the specific volume form there of the Euler equations, we would get a system of the form that I showed on the previous slide with the h. In fact, I believe we wouldn't have any a terms, but we would have the hx squared terms. Okay, so that seems great. And you say, well, that's nice, but I don't want to solve the Euler equations. That's a trick that exists for the Euler equations. So it turns out this idea of variable manipulations to expose system structure actually is much more general and much broader. And this is the notion of lifting. So I should say that I believe the term lifting goes back to McCormick from the 70s, where he was performing variable manipulations and introducing auxiliary variables to optimization problems to expose convex structure. And again, to look at another community, the operations research community is a community that does an amazing job of first manipulating their problems to expose structure that then their algorithms can exploit. So what is lifting? Lifting is this idea of introducing auxiliary variables to expose structure in a nonlinear problem. Here's a really simple example to illustrate it. If we think of a scalar nonlinear ODE, x dot equal x to the 4th plus u, so x here is just a scalar. We introduce auxiliary variables. W1 is x squared and W2 is W1 squared. We need now evolution equations for dW1 dt and dW2 dt, so it's just a matter of applying the chain rule and substituting. We find that the dynamics for W2 have an x times W1 times W2, so this is a term that's cubic in now this lifted state. We introduce an auxiliary variable, another one, W3, which is x times W1. Again, apply the chain rule. And end of story. You could either write your equation as the scalar quartic ODE at the top of the slide, or you could write it as a system of 4 quadratic bilinear ODEs. Quadratic bilinear, quadratic means that if you look now at this new state, this lifted state, x, W1, W2, and W3, you see that the equations only have quadratic at most products of the state, and then the bilinear part refers to the terms where there's a product of a state times the input u. What we also notice is that if you were willing to accept a system of differential algebraic equations, you could actually have stopped at just introducing the one auxiliary variable W1 and have the QBDAEs. So again, this seems like a simple example. It turns out if you start looking at systems of partial differential equations, there are many, many, many different kinds of partial differential equations that can be lifted into a polynomial form, and in particular into a quadratic bilinear form. I'm not going to go through the details, but just to emphasize how general this idea is, here's a simple model of a tubular reactor, and you can see up there at the original equations, you can see there's a 1 over Peclet number, there's a second derivative, a diffusion term, there's an advection term, and then there's the nonlinear term, which has the state, the concentration, e to the gamma minus gamma over temperature. So there's a 1 over state inside an exponential being multiplied by another state. You can introduce auxiliary variables. We go through, we have to introduce W1, W2, W3, W4, W5, W6, 6 auxiliary variables. We end up with some algebraic equations, but we can write those nonlinear equations in quadratic bilinear form. Okay, so that's great. So we have the notion of projection. We have a way to write our systems in polynomial form that we can then exploit because we know that we can do the projection in a way that preserves that form. But we need one more ingredient, and this is where the machine learning, the data-driven perspective comes in. Because can you imagine what would happen if I showed up at the Air Force and said, by the way, you guys have just spent a decade on the CFD model, you got it wrong, you got to rewrite it, and you've got to use 1 over temperature and e to the temperature and 1 over temperature squared as variables. They would literally throw me out of the door. So clearly it's not viable, nor is it even mathematically well-founded to think about discretizing the PDEs in these lifted variables. But this is where the perspective of learning from data can come into play. So this last ingredient is a method that we call operator inference, which is to say learn the projection-based reduced models, but rather than doing V transpose AV, do it by running the high-fidelity model, the full model system, generating snapshots, and then learning directly the A-reduced, learning the A-reduced. And what we can show is that under some certain idealized conditions without noise, we actually can recover the V transpose AV we would have gotten to if we'd done it intrusively. But the trick is we don't need A or H. We don't need to know exactly what the operators are. We don't need to go into the code and do the projections. And again, you can see how this is going to be powerful when we want to work with lifted versions of codes that we actually don't have. So let me show you how operator inference works. So let's first just think about a full order model. And again, let's work with this quadratic structure of the full model. So the operator inference question says, if I gave you state data, if I gave you snapshots, X, at different times here, T1 through TK, so these are the full state solutions. And I'm also going to need the time derivatives. The machine learning folks would call this the velocity data, so the time derivatives of the snapshots. Could you tell me the operators E, A, B, and H of the system that produce the data? And so you could write down a least squares problem that states that, says, find me the operators A, B, E, and H that minimize the residual. And what's the residual? The residual is taking the form of the governing equation and plugging in the X and the X dot data that I've collected and minimizing sort of summed out over here over all the snapshots. So the reason we write this as a minimum residual problem is that this least squares problem has a ton of structure and can be broken apart. In principle, you could do this for the full model, but we're not interested in learning the million by million dimensional A. What we're after is the reduced model. So we pose the same problem, but now we say, if you were given reduced order data, so simulations from a reduced model, could you learn the dense, small, reduced E hat, A hat, B hat, and H hat that produce the data? And again, the least squares problem has exactly the same structure. So again, this is the operator inference approach that Benjamin and I worked on together several years ago. And again, I'm not going to present the theoretical details, but under certain idealized conditions, in doing this, we can actually, the A hat that we learn, that we recover from the data, we can show it converges to the V transpose AV, the A that you would have gotten through the intrusive projections. But all we need here is the data, is the snapshot data coming from the code. Okay, so now we have all the ingredients. Let me put them all together for you in this method that we call lift and learn. And again, variable transformations sit at the heart because the variable transformations are what expose the system structure. The notion of projection is what lets you embed that structure in your reduced models, embed the physics. And then the non-intrusive learning is what lets you, now it frees you. It frees you from having to work with mass, momentum, and energy because that's what the code was written in. The non-intrusive learning frees you to work with whatever variables make the problem, expose the structure in the problem. So again, we start off with full state trajectories. We take this giant code, we run it, we generate snapshots. These are the x, the state vectors at time here t1 to tk. We also need the time derivatives, the x dots. Now the second step is we've got our pencil and paper out. We have the governing equations that we know we're solving, we know we want to solve. We can analyze those governing equations and identify the variable transformations that would, again, expose the system structure. So introducing auxiliary variables, maybe working with things like 1 over density instead of density, whatever it is, we're going to identify those transformations with pencil and paper from the PDEs, and now we're going to apply those transformations not to the model, but to the data, to the snapshot data that's been generated in step 1. So that now gives me the snapshot matrix, the capital X, and its derivative that I need to work with for learning the reduced models. So from that now transformed snapshot data, I can compute the POD basis. I compute, like I said, in what I'm showing you today, we're working with a linear subspace, so we compute the POD basis. Now we can take the lifted trajectories, we can just project them onto the POD basis. So that's nothing but V transpose X. Again, this is non-intrusive. This just says take the data that you generated and figure out its representation in the POD space. And so now what that generates for me is the X hats. These are reduced order trajectories that look like they came from a reduced model of a lifted system. But they're generated from the original system, transformed, and then projected. So I have now the data that I need for that least squares minimization problem, and I can say, now find me the A hat, B hat, E hat, and H hat that defines the reduced model that could have produced that data. And again, why is it that I'm looking for the quadratic form? I'm looking for the quadratic form because in step number 2, I've identified the right set of variables to work with that tell me that this is the form of the model I should be looking for. So all those ingredients together, it gives you the convenience of black box learning. And what I'm going to show you, the example from the Air Force, we do not have access to the code. Literally, somebody ran the code for us, generated the snapshots and the data, and we were able to derive the reduced models without ever having to do anything with their big, giant finite volume code. So it's got the convenience of black box learning, but it inherits some of the rigor of projection-based model reduction. In particular, with projection-based model reduction, the notion of error estimators that are out there for a large class of problems through this rigorous approach of projection for creating the reduced models. And again, we're putting the structure into the reduced models. It may be that neural networks are very expressive, but when the governing equations tell us that the state evolves with linear and quadratic dynamics because of governing principles, I believe that embedding that into a reduced order model is actually what's going to give us predictive power. So we get the kind of I would say, the benefits of both worlds. So let me show you one example of how this approach works. I should say we've tried this approach on lots of different problems. The one that I'm going to show you, the results are not the best results, as in they're the ones that perfectly overlay the model, but this is by far the most challenging problem. And the results that we have here from the reduced models, the lift and learn reduced models, are by far the best model reduction results that anybody has been able to get for problems of this nature. So we're modeling a single injector of a rocket engine combustor. So just one injector of the schematic there on the right-hand side. Again, the governing equations are conservation of mass, momentum, energy, and species. There's a few details there. I should say we're doing a 2D problem, 2D which will run much, much faster than 3D and give us more data to work with. the setting in this case is that the injector is forced by a back pressure boundary condition that's inducing some oscillations in the combustor. So as I mentioned, we don't have access to the code. We have training data and we have test data. The training data is 1 millisecond worth of data, of snapshots, and with a time step of 10 to the minus 7, that's 10,000 snapshots. And that took about 200 hours of CPU time for somebody to generate. Now, for this particular problem, I talked about the liftings and exposing structure. So there are liftings that would make those governing equations completely quadratic, make them quadratic, introducing some algebraic equations. And what I'm going to show you here, we've chosen not to do the full lifting. Instead, we work with just the 4 variables showing there, the pressure, the 2 velocities, the 1 over density, the specific volume, and then the 4 species concentrations. And it turns out that just by using those 8 variables instead of the original conservative variables, many of the terms in the governing equations become quadratic. Actually, a remarkable number of terms in the governing equations become quadratic. There are a few terms that don't become quadratic. We decided to learn quadratic reduced models, and so we're going to be incurring a little bit of error in approximating those nonlinear terms. And then you see there the dimension of the snapshot matrix. So that's the training data. The test data, we have another millisecond of test data, and we have something went a little astray on that slide. That's all right. We have another millisecond of test data, and you'll be seeing test data at 4 monitor locations. Okay, so here's one example of how the lift and learn reduced models perform. So what we're looking at here is in blue, and the blue dashed lines is the reduced model. It's got a dimension of 17, so 17 POD basis functions. In red is the truth, the results from the full CFD code. And what we're looking at is the pressure trace versus time at that monitor location there at the top of the injector. The first half of the plot is the training data. So those are the data that went into building the POD basis and learning the reduced models. And then the second millisecond there is the test data. So, and we didn't even see the test data before we created these reduced models. So you can see the reduced order model does a pretty good job. You can see the phase is off by a little. If we increase the dimension of the reduced model to 29, we're actually able to capture the phase very well. You can see that some of the magnitudes and the pressure oscillation, there's a limit cycle oscillation set up in this injector, are not captured perfectly. But overall, as I said earlier, this is a really amazing performance for a reduced order model for this problem. And again, just to give you a sense of just how well the reduced model does, sort of remarkably well, here are a few snapshots. At the top is the CFD, the full order result. In the middle, the predictions from the reduced models with 29 modes, and then on the bottom, a measure of error. And what we're looking at here is the pressure on the left, the temperature on the right. And so first of all, you see there's a lot going on in this problem. There's a lot of small-scale structure. You can see if you look really closely that the reduced model is not perfect. It certainly doesn't get all the details, and we don't expect it to. But you can see again how well it actually really does. And here are the similar plots for the methane, the CH4, and the O2. And again, a lot going on. The reduced model is not perfect, but it's remarkable just how well it does. And why does it do so well? Why does such a small reduced model do so well? And why does it do so much better than the POD dime methods that everybody's been trying? I believe it's because of those variable transformations that have exposed the system structure, and just this relatively sort of simple and maybe in retrospect obvious thing of working with 1 over density instead of density makes a huge difference to being able to learn low-dimensional models. Okay, so let me just wrap up with a few conclusions. First, I just want to take you back to where I started with the talk, predictive data science, a convergence of data science and computational science and engineering, that this is absolutely essential if we're going to be using data to drive high-consequence decisions across science, engineering, and medicine. And I hope through the particular focus on model reduction, I've showed you one way to make concrete this idea of bringing the perspectives of machine learning and data science together with perspectives of computational science and engineering, one way that manifests itself. Why do we need to learn from data through the lens of models? We have to do this. We have to exploit the structure of the problem to make, otherwise these problems are intractable. And no amount of data, no more and more and more data are going to solve our high consequence problems in science, engineering, and medicine if we don't have the models. We need to respect physical constraints. We need to embed domain knowledge. We need to bring interpretability to the results. We need to be able to deal with heterogeneous, noisy, incomplete, maybe big data, but relatively sparse data. And we need to be able to quantify the uncertainties in our predictions. So maybe just a last comment. This talk is focused very much on research, but I didn't want to let the talk go by without mentioning the term education. Everything that I've talked about today is so interdisciplinary. Computational science and engineering is already an interdisciplinary field that brings together mathematical modeling, computer science, and applications across science, engineering, and medicine. We need to throw statistics, machine learning, all these other pieces into the mix. And I think now more than ever, we absolutely need interdisciplinary, both research and education, that really is at the interfaces. So with that, let me close. If you'd like to know more about some of the especially technical work that I talked about today, you can find it at kiwi.odin.utexas.edu. And as I mentioned, both Boris and Parisa are here. You could also chase them down on a break and ask them questions. But with that, I'd like to thank you, and I'm not sure, I think I'll be happy to take questions.